Welcome to Year 8 Competence Middle Years Program Level 3 Sciences. This is going to be lesson number 5.1, which is an illustration for the laboratory activity. So let's start. We're going to do an introduction to the fountain design, which is activity number 3. So let's first of all consider a fountain, a beautiful fountain, a fountain like this one. Is it not nice with its jets and everything? Let's now focus on the most interesting bit for us, which is of course the water jet. If we analyze what the water jet looks like, we will see that it very well fits a parabola. Look, if we draw a parabola, it absolutely matches the trajectory the water has. Now we draw the axis, the horizontal axis and the vertical axis. It's not that easy working on the picture, so let's create a replica of that water jet. We have it in the image. And now, if we enlarge it, we will be able to do a more accurate analysis. Let's now analyze our jet. We will draw an enlarged version of the scheme on the previous slide. First of all, we need to define the senses, on each axis. For the vertical one, we will choose upwards because the motion starts going up. And on the horizontal axis, we will choose towards the right because that's the displacement we have. Second, we set the origin of coordinates. The origin of coordinates will be the origin of the motion because that will make things easiest for us. So now we have our reference system. Let's get into the motion itself. At the initial point, we have the initial speed. Velocity is always tangent to the trajectory in any movement, any kind of shape the trajectory has. So to define the initial velocity, we will draw an arrow tangent to the trajectory on the original point, on the origin of the trajectory. We will call that V0, initial velocity, and we will call V0 with a small arrow on top to mean that it has an orientation. Remember, never forget the small arrow because you would be beheading the velocity and it's not nice going around beheading people. Now we find the components. To find the components, we draw the perpendicular to the axis from the end of the arrow. So we draw first the perpendicular to the x-axis and we find V0x, which is in green in the scheme, and then the perpendicular to the y-axis from the end of the arrow to find V0y. Therefore, V0x, as we saw in the previous lesson, is V0, the length of the arrow, times the cosine of the angle it forms with the horizontal, which is alpha, and it corresponds to the contiguous side to the angle, whereas V0y is V0 times the sine of the angle, and it corresponds to the opposite side to the angle. As soon as water comes out of the tube, the only effect on each drop is gravity, and gravity pulls down along the vertical axis. Therefore, there's nothing affecting the horizontal axis, and because of that, we have a uniform rectilinear motion along that axis. The expression for position in uniform rectilinear motion, as we know, is x equals x0 plus v0x times time, which is v0 cosine of alpha times time, because x0 equals 0. The origin of the motion is the origin of coordinates. Along the vertical axis, though we do have the acceleration of gravity, and it's a constant acceleration. Therefore, along that axis, we have a uniformly accelerated rectilinear motion. The expression for the position at each value of time in UARM is y equals y0 plus v0y times time plus half the acceleration times time squared. Now, we know that y0 is 0 because it starts at the origin of the coordinates. We know that v0y is on the positive part of the vertical axis because it starts going up, but we know that gravity is pulling down. So we will put that negative sign and then we will use g as 9.8. It's always convenient to put the sign outside the value. Therefore, y0, v0y positive, acceleration negative gives us this expression, v0 sine of alpha times time minus, because the acceleration is downwards, half of g, 9.8, as we will see, times time squared. Let's assume that our jet has an initial velocity of 3 meters per second. It has a 60-degree inclination above the horizontal, and then the final height reached, meaning the bucket, the basin where we are collecting the jet, is at 10 centimeters above the origin. So it's 10 centimeters higher, 0.1 meters higher than the origin of the jet as we were representing. We remember, as we saw it in the previous lesson, that the sine of 60 degrees is 0.866 and the cosine is 0.5. We draw our scheme. We see that the jet ends above the origin, and those are the 10 centimeters, the 0.1 meters. Let's start calculating the components of the initial velocity. V0x, as we know, will be V0, the length of the arrow, the modulus, times the cosine of the angle, because it is the contiguous side to the angle, cosine of 60. That means 3 times 0.5, which is 1.5 meters per second. V0y instead is the modulus 3 times the sine of the angle, which is 3 times 0.866, and that gives us 2.598, which we round up to 2.6 meters per second. It is higher speed along the y-axis at the origin than it is on the x-axis, and as we can see in the figure. So now we've arrived to the point where we must ask Dr. Mathematics the question. We know that we are collecting the jet 0.1 meters higher than it was launched, that the initial speed is 3 meters per second, and that the angle is 60 degrees. We know the final height, but we do not know the final distance from the origin along the x-axis. We will mark that point with a black dot on the scheme. We need to find which is the horizontal distance at which the jet finds itself when it is 0.1 meters above the origin. The Dr. Mathematics answer will be to this question: what is the value for x, distance of the horizontal axis, at which the jet finds itself when the height is 0.1 meters. In order to find that, we need to make a previous step, which is calculating the time it takes us to reach that point. Therefore, we will rephrase the question as what is the time taken by the jet to go from height 0, which is the origin, to height 0.1 with a uniformly accelerated rectilinear motion, which is the kind of movement we have along the y-axis. We write the equation y equals y0 plus v0y times time minus, because it pulls down, a half of gt squared. Y0 equals 0, therefore the next step is v0 sine of alpha times time minus a half of gt squared. Final position 0.1. So y equals 0.1 equals 3 times 0.86 v0 sine of alpha times time, which we do not know, minus a half of 9.8, the modulus of gravity going downwards, times t squared. We rearrange the equation, passing 0.1 to the other side with the opposite sign. So we have 0 equals minus 0.1 plus 3 times 0.88 times time minus 1/2 of 9.8 t squared. So let's recopy our equation. 0 equals minus 0.1 plus 2.6 times time minus 4.9 times time squared. We can work with the equation the way it is. It is normally easier if we have the coefficient of t squared with a positive sign. Therefore, we can multiply the entire equation times minus 1 and change the sign of each and every term in the equation. If we do that, we obtain that 0 equals 0.1 minus 2.6 times time plus 4.9 times time squared. Dr. Mathematics, which is a great friend of us, and he will become even greater friend, would tell us that this is a quadratic equation, and the general expression of a quadratic equation is 0 equals a times x squared, the coefficient of the unknown squared being a, plus b times x, the coefficient of the unknown to power 1 being b, plus c, which is the independent term. And we call it independent term because it is not multiplying x. In our case, we have that a equals 4.9, which is the coefficient of t squared. B equals minus 2.6, which is the coefficient of t, and the independent term is 0.1. For a quadratic equation like this, the solutions come from the following expression, which we will study in mathematics. T, the solutions, equal minus b minus plus the square root of b squared minus 4 times the product of the coefficient of the squared unknown and times the independent term, all that divided by twice the coefficient of the unknown squared. If we now replace the values we have in our equation in this expression, minus b being minus 2.6 equals 2.6, minus plus the square root of b squared minus 2.6 squared, minus times minus is plus, it's the same as 2.6 squared, minus 4 times a, which is 4.9, times c, which is 0.1, all that divided by 2 times a, which is 4.9. We do the multiplications and we square 2.6 and we obtain 2.6 minus plus the square root of 6.76 minus 1.96 divided by 9.8. That means we do the subtraction, we do the square root, it means 2.6 minus plus 2.19 divided by 9.8. So we have a first value of time obtained from this expression, which is 2.6 minus 2.19, all that divided by 9.8, and the value is 0.04 seconds. And we have a second value of time, which is 2.6 plus 2.19, all that divided by 9.8, and that gives us 0.5 seconds. Let's now analyze what that means. Again, the question we have asked Dr. Mathematics is, at which value of time does a water drop launched from the origin of coordinates at 3 meters per second, 60 degrees above the horizontal, reach height 0.1? What's the meaning of this? Dr. Mathematics is telling us, if you launch a water drop at 60 degrees above the horizontal and 3 meters per second, it reaches the height 0.1 at 0.04 seconds and again at 0.5 seconds. Obviously, since we are launching it and then it comes down, the value we are interested in is 0.5 because it's the second time it reaches height 0.1 when going down, and that is, from the scheme, the moment, the instant we are looking for. So to now find the distance on the horizontal axis that the water drop has covered whilst doing that movement, we insert the value of time in the expression of the distance covered along the horizontal axis, which has uniform rectilinear motion. That means x equals x0 plus v0x times time. X0 was 0 because we were at the origin of coordinates. So we have 1.5 times 0.5, and that gives us 0.75 meters, meaning the black dot on the scheme we have on the slide is 0.1 meters high, and it is 0.75 meters distant along the horizontal axis from the origin of coordinates. So, to summarize, the black dot on the scheme lies at 0.75 meters far from the origin along the x-axis, and it lies at 0.1 meters high from the origin along the y-axis. That is where we need to place our bucket if we are going to receive the water jet at that point. As an extension to this problem, let's analyze what would happen if the question we had asked Dr. Mathematics were, what would be the distance along the x-axis at which we should have put our bucket if we wanted to collect our water jet not at 0.1 meters high, but at 0.5 meters high, quite farther away. The components of the initial speed would be the same, 1.5 meters per second along the x-axis and 2.6 meters per second along the y-axis. And we would replace, instead of the 0.1, the 0.5 meters in the y on the equation. Therefore, the equation would be 0 equals minus 0.5 plus 2.6 times time minus 4.9 times time squared. Now we change the sign of the entire equation and we have 0 equals 0.5 minus 2.6 times time plus 4.9 times time squared. The solution again comes from the expression time equals minus b minus plus the square root of b squared minus 4 times a, the coefficient of t squared, times c, the independent term, the independent coefficient, all that divided by twice a, the coefficient of time squared. We replace the values and we obtain 2.6 minus plus the square root of 2.6 squared minus 4 times 4.9 times 0.5, all that divided by 2 times 4.9. When we solve the square and the multiplication, the product, we obtain 2.6 minus plus the square root of 6.76 minus 9.8 divided by 9.8, which equals 2.6 minus plus the square root of minus 3.04 divided by 9.8. But we cannot solve the square root of a negative number. There's no real solution for the square root of a negative number. Therefore, Dr. Mathematics is telling us, if the question is at which distance or at what time it takes for a water drop launched at 3 meters per second, 60 degrees above the horizontal, to reach 0.5 meters high, the answer is non-existent. It does not exist. And now we need to apply our critical thinking, our reasoning, our understanding of nature. So we are launching a water drop 3 meters per second, 60 degrees above the horizontal. We are asking Dr. Mathematics how long it takes that water drop to reach 0.5 meters high. And Dr. Mathematics says, no, it does not exist. What can we interpret? The only possible interpretation is it does not reach that height. Let's double check that, because we know the formula, we know the expression that gives us the maximum height a water jet or a parabolic motion reaches. We've seen that h equals v0 squared times the sine of the initial angle squared divided by 2 times gravity. If we replace our values, v0 squared is 3 squared, the sine squared is 0.866 squared divided by 2 times 9.8, and that gives us 0.11 meters. We had already solved this problem. So the maximum height is 0.11 meters. That's why we can calculate the time it takes the water drop to reach 0.1 on its way up and on its way down. But we cannot calculate, we cannot find a value for the water drop to reach 0.5 because it does not reach 0.5. Therefore, Dr. Mathematics tells us no answer to that question. That is the beauty of science. Therefore, as always, enjoy.